Welcome to this QOD video on chemical kinetics. I have started a few of these videos with just sort of random YouTube videos for you to watch. I actually do have some YouTube videos here for you to watch, but these actually have something to do with the subject of the video itself. So enjoy this medley of kids playing balloon stomp.
Get set, go! Stay in the white circle! Stay in the white circle! Stay in the white circle! Matt, keep hopping! Keep hopping, Matt! Keep hopping, Matt! Stay in the white circle!
And only use your feet to stop them. Only your feet. Stay on your feet. Keep going. Keep going. You're still in, Rain. You're still in.
And there actually was a point to watching all those, and I promise you that I will get to the point of what that was in just a few minutes. So this video is about chemical kinetics, and when you think about kinetics, I think what would probably first come to mind, if you didn't know better, was just the concept of kinetic energy, and that is the energy associated with movement of things. In chemistry, when we talk about chemical kinetics, we're actually talking about something else, and that is we're talking about the rates at which chemical reactions occur. And so the study of chemical kinetics is the study of rates of chemical reaction. And it's important to understand that there's actually not a correlation between whether or not a reaction is spontaneous and whether and the rate of the reaction, that is, whether it occurs fast or slow. So there are lots and lots of spontaneous reactions that occur very quickly, like burning gasoline. And then there are lots and lots of spontaneous reactions that occur very slowly, like rusting of a large piece of iron. And so whether or not a thing is spontaneous actually doesn't tell us anything about how fast it's going to occur. And so when we study rates of chemical reactions, we study the various things that affect the rate. In other words, we can make reactions go faster or slower. And the ways in which we make reactions go faster or slower can tell us some things about that reaction, including helping us elucidate what we call the mechanism of a reaction. And that is, a reaction mechanism is simply the series of single steps that make up the total reaction and tell us how it actually occurs. So let's talk about some things. I just said that we can affect the rate of a reaction. Let's talk about some things that actually do affect the rate of chemical reactions. And one of those would be the physical states of the reactants. Chemical reactions occur when chemical molecules or particles collide with each other. And so the easier it is for particles and molecules to collide with each other, the faster the reaction is going to go. And so if we have reactants in solution, say in the same phase in a homogeneous mixture, whether that would be something like air or in an aqueous solution or in a solution in an organic solvent, then those things are going to react the fastest. So the more homogeneous we can make that mixture of reactants, the faster that those molecules will react. So for example, if we have two things in the gas phase, those things are going to bop into each other fairly consistently, and so they'll react quickly. If we have two things in an aqueous solution, they're going to tend to react with each other pretty quickly. If some things that would tend to slow a reaction down would be, say, something in a liquid reacting with a solid that's heterogeneous solid that's inside the liquid. And probably the thing that would react the slowest would be trying to get two solids to react with each other, because they can only contact each other in a very limited way. And so if you have a heterogeneous reaction in which it's difficult sometimes for the particles to get together, the more finely divided we can make a solid reactant, the faster that reaction is going to be. And if you think about the difference between if you have iron powder and you sprinkle it over a Bunsen burner flame, that will actually burn pretty quickly. Whereas if you stick just an iron shot put into a Bunsen burner flame, you're essentially not going to get any combustion at all.
Maybe because it's smaller?
Yeah, it is.
That was an example of burning some iron filings. So what are some other things that affect reaction rates? Temperature. So a reaction is always going to run faster at a higher temperature because the reactant molecules or particles have more kinetic energy, and so they're moving faster. They're going to collide with each other more often, and they're going to collide with more frequently with the energy needed for the reaction to occur. One of the most important things that we can talk about that affect reaction rates, and what the real focus of this chapter is concentration. And that's probably the most important thing that affects the rate of a reaction. So if we increase the concentration of reactants, we're going to increase the frequency with which they collide, and we're going to increase the frequency, the rate at which they react with each other. And so here's a slightly different example from what you were just seeing of burning iron filings. If you take a piece of steel wool and you heat it up in a Bunsen burner, it will glow red, but it's only going to burn really, really slowly. But if you take that same piece of red hot iron and you stick it into a flask that contains, instead of just air, which is only 20% nitrogen, that is only 20% oxygen, and you put that instead into a flask that has 100% oxygen, that's going to burn really quickly. And that's because you've increased the concentration of one of the reactants, in this case the oxygen. And so that increases the rate of the reaction. One more thing that'll affect the rate of a reaction would be the presence of a catalyst. If you've had biology, you may be familiar with enzymes, which are biological catalysts. And so their job is to speed up reactions. The main thing about a catalyst is that it is neither a reactant nor a product in a chemical reaction. It changes the mechanism of the reaction, but it's not consumed over the course of the reaction. And when the reaction is over, you can recover the catalyst unchanged. So let's talk about reaction rates and how we determine reaction rates. And so the main way in which we do this is to monitor a reactant or a product and literally determine over a course of time how fast that reactant or product is either disappearing or appearing. And so if we're looking at the red balls here, which are reactant A, and so presumably this reaction is A goes to B, and you can see in the beginning there's all A and no B, and then after 20 seconds there's about a 50-50 mixture of A and B, and then after 40 seconds there's quite a bit more B than A. So we can monitor either the disappearance of A over time or the appearance of B over time, and that is a way in which we can help to determine the rate of the reaction. And in general, reaction rates are going to decrease over time. And so that is why I started out by showing you those pictures of the kids playing the balloon stomp, because reaction rates are dependent on concentrations of reactant. And so if you think about what happens to the concentrations of the reactants over the course of the reaction, they go down. And so as the concentration of reactions go down, then reactants go down, then the rate of the reaction goes down. And we can think about this in terms of the balloon stomp. In general, if you're watching a balloon stomp game, what you're going to see in the beginning is there are a lot of kids and there are a lot of balloons, and so they're going to get popped fairly quickly. As the reaction goes along, as the game goes along, there are fewer balloons to be popped, and there are fewer kids to pop them. And so you would expect that the rate at which balloons get popped is going to go down with time, unless you're this girl. Let's look at some actual data we might collect in order to try and determine the rate of a specific reaction. And this is a fine organic reaction in which we're taking butyl chloride and reacting that with water to give butyl alcohol plus hydrogen chloride. And so what is happening in this table is we are measuring the concentration of butyl chloride as a function of time. And you would imagine that as the reaction progresses, it goes down. And so we're looking at what the concentration of butyl chloride is every 50 seconds. And in the beginning, it's 0.1 molar, and then it goes down, and then after 50 seconds, and then down some more after 100, and down some more after 150, et cetera. And what we can do is actually calculate average rates of disappearance of the butyl chloride over each span of 50 seconds. And we do that simply by taking the change in concentration of the butyl chloride, which would be 0.0905 minus 0.1, over the change in time, which would be 50 minus 0. And that gives us an average rate of disappearance over that span of 50 seconds. Now, by convention, reaction rates are always reported as positive values. And so even though 0.0905 minus 0.1 gives you a negative number, you would simply report that as a positive value. So over the first 50 seconds of the reaction, the concentration of the butyl chloride is going down by 1.9 times 5 times 10 to the minus fourth moles per liter per second. And then you can see over the next span of 50 seconds, it goes down by 1.7 times 10 to the minus fourth, and then 1.6. And again, we're seeing that the rate of the reaction is decreasing as we go along. The average rate of reaction over the first 50 seconds is greater than the average rate of reaction over the second 50 seconds, et cetera, et cetera, et cetera. And so we notice that the average reaction rate decreases, and that's because, again, as the reaction proceeds, the concentration of both butyl chloride and water decreases. Since reaction rate is going to be, in general, dependent on reactant concentrations, as their concentrations go down, we would expect the rate of the reaction to decrease. Now we can take that tabulated data that we just showed and actually graph it, in which we are graphing the concentration of butyl chloride as a function of time. And you will see, again, you get this kind of curve. You see it's not a constant reaction rate. The concentration of butyl chloride is not going down in a linear fashion as a function of time. It is slowing down as it goes. And so we can talk about various types of rate. What we were just doing a moment ago was looking at the average reaction rate. That is the slope of a straight line between this point and that point, and then the slope of a straight line between this point and that point, and the slope of a straight line between this point and that point, etc. Those are average rates. We could determine the average rate over the first 800 seconds, and that would be the slope of a straight line between that point and that point. But there are other ways in which we can talk about a reaction rate as well, and that would be instantaneous rate. And so, for example, if we just took this point at 600 seconds, we could calculate the instantaneous rate. It would require us to have calculus to do this, but it would be to determine the slope of a tangent line to this curve at the 600 second point. So that's the concept of instantaneous rate. So average rate is a straight line between any 2 points is going to tell us the average rate over that stretch of time. Instantaneous rate is going to be a tangent to the slope of the line at any particular point. And then there's a third type of rate that we talk about, which is initial rate. An initial rate is actually just simply the instantaneous rate at the very beginning. So here in this sort of light brown colored triangle here, they're trying to describe to you what's called the initial rate, which is simply a special case of the instantaneous rate. It's an instantaneous rate when T is equal to 0. Okay, so I mentioned to you that that rates are always expressed as positive numbers. And so if we're monitoring the disappearance of the reactant, which in this case is butyl chloride, it's always going to be the change in concentration of butyl chloride over the change in time. But in order, by convention, to make it positive, because the change in butyl chloride is going to be a negative value, that is, its concentration is decreasing, we always multiply that by -1. If we were monitoring the appearance of butyl alcohol, which is the major organic product of this reaction, it would simply be the change in butyl alcohol concentration versus time. If we graph that, it would actually be going up in exactly the opposite way as the butyl chloride concentration is going down. Its concentration change would be positive. Therefore, we don't need to put a negative sign in front of it because it's going up with time. Therefore, we would get a positive rate. But because these have the same stoichiometric coefficient, then this is being formed at exactly the same rate that this is disappearing. And so we could use either one of them interchangeably as a marker for the reaction rate. Well, what if we're talking about things that do not have the same coefficient in the balanced equation? How then do we equate them when it comes to measuring reaction rate? Think about this particular reaction in which two molecules of hydrogen iodide are decomposing into hydrogen gas plus iodine gas. And if you think about the rate at which this reactant is disappearing versus the rate at which a particular product is appearing, you have to realize that because there's a 2 in front of this is actually disappearing. The HI is actually disappearing twice as fast as either H2 is appearing or I2 is appearing. So if we just talked about the rate of disappearance of this substance versus the rate of appearance of either one of these, we'd get different numbers. These are going to appear only half as fast as this is disappearing. And so the way we account for that is simply to, when we're talking about the change in concentration of any substance, whether it's a reactant or a product, we divide it by its coefficient of the balanced equation, and that therefore gives us a number which is going to be equivalent in each case. So let's say this is disappearing at 0.2 moles per liter per second. Well, each of these is going to be appearing at 0.1 mole per liter per second because they're only appearing half as fast as this is disappearing. And so if we divide this by -2, negative 0.2 moles per liter per second divided by 2 gives us 0.1 moles per liters per second. These, which are appearing at 0.1 moles per liter per second, when divided by their coefficient, are still going to give us 0.1 mole per liter per second. And so we get the same, we're going to get the same number no matter which one we look at, whether it's the disappearance of HI or the appearance of H2 or the appearance of I2. Well, that's a lot of talking, and this may be getting just a little bit confusing, but let me give you this general equation, and then I will try and show you an example of how this works. For any general reaction in which A plus B are going to C plus D, the capital letters represent the substances. The lowercase letters represent their coefficients in the balanced equation. If we are determining the reaction rate based on monitoring the disappearance of any reactant, first of all, we're going to put a negative sign in front of it because once more, the change in concentration of that thing is going to be negative because it's disappearing. And so we put a negative sign in front of that negative to make it a positive number. And we divide it by its coefficient of the balanced equation. Same thing with B because it is also a reactant. We put a negative sign out front because reactant concentrations decrease. Therefore, those deltas are negative. And so to make the rate positive, we have to make a negative negative. And we're going to divide that by its coefficient in the balanced equation. If we're looking at a product, whether it is C or D, We don't put a negative sign in front of it because the change in concentration of products over time is a positive thing. And so we don't have to multiply it by a negative to get a positive number for the rate. But we are in each case um, going to divide that thing by its coefficient of the balanced equation, so that we'll end up getting the exact same number, whether we're monitoring the disappearance of A or the disappearance of B or the appearance of C or the appearance of D. At this point, I'm sure that more than one of you is probably scratching your head and thinking, what the heck is he talking about? Because this whole business of stoichiometry and rates falls into the category of what chemists often refer to as hand waving, which means a lot of talk, but no data. So let's try applying some data to this. Let's take a specific reaction. This reaction of bromine gas with nitrogen monoxide to give, I don't even know what the name of this thing is called, nitrosyl bromide, I believe is what that's called. Anyway, I picked this because the coefficients are not the same for everything. So the coefficient of 1 for the bromine, 2 for the nitrogen monoxide, and 2 for the nitrosyl bromide. And then I went ahead and just created some data. So let's suppose that at the beginning of this reaction, when T is equal to 0 seconds, nothing has happened, and I've put into the reaction flask a 0.4 molar bromine and 0.4 molar nitrogen monoxide, and of course there's none of the product because nothing has happened yet. And let's just say that after 50 seconds, some reaction has occurred. And so now the concentration of the bromine is 0.3 molar, the concentration of the nitrogen monoxide is 0.2 molar, and the concentration of the product is 0.2 molar. And that makes sense because these things have to be consistent with the coefficients in the balanced equation. If this concentration goes down by 0.1 molar, this concentration has to go down by 0.2 molar because this is disappearing twice as fast as that is. And the concentration of the product has to change at the same rate that the concentration of the nitrogen monoxide is changing because they both have the same coefficient. And so now if I actually calculate the average rate of reaction for each of those species over that 50 seconds, it's going to be the change in concentration divided by the change in time. So for the bromine, it's final minus initial concentration over final minus initial time. That gives me a value of negative 0.002 moles per liter per second. For the nitrogen monoxide, it's final concentration minus initial concentration over final time minus initial time. That gives me a change in concentration of negative 0.004 moles per liter per second. And for the product, it's final concentration minus initial concentration over final time minus initial time. That gives me a average change in concentration of 0.004 moles per liter per second. And as you'll see, as we've been saying all along, for reactants, that would give you a negative number because the change in the concentrations are going down. And for the product, that would give you a positive number because the concentrations are going up. But now if I divide this by -1, because for reactants we always multiply by -1 and divide by the coefficient. So that's the same as dividing by -1. Here I'm going to divide by -2, which is multiplying by -1 and dividing by 2. Here I'm going to divide by 2 because we don't multiply product by -1. We just divide them by their coefficient. And in each case, then we get the same number. So this is our normalized rate for the reaction for over that first 50 seconds, 0.002 moles per liter per second. Well, the QOD is going to really focus, I think, more on just practical issues of what is rate, how do we, what are some things that affect rate, how do they affect rate. I doubt that I'm going to be asking you to do a calculation like this on the QOD, but this will come up in quiz and test questions. So I'll give some suggested problems, and thanks so much for watching.